LLMs trained on world knowledge are already strong at many tasks. Their reasoning can be further improved by training on proprietary, task-specific data. Fine-tuning, a type of transfer learning, is widely used in deep learning. Unlike pre-training, which builds general reasoning, fine-tuning focuses on specific domains. Let's dive deeper to understand the fine-tuning. For LLMs such as ChatGPT, the underlying model is based on the decoder architecture of the transformer. It is first pre-trained on a large, unlabeled data corpus using significant computational resources. Next, it is fine-tuned on a smaller, labeled dataset. Fine-tuning requires less technical expertise, computation, and data, making it accessible to more people, unlike pre-training, which is limited to large companies. Fine-tuning LLMs involves several techniques, including supervised fine-tuning, reinforcement fine-tuning, and reinforcement learning from human feedback, etc. These methods are often combined and used iteratively to improve the model's reasoning abilities. We will explore these techniques in more detail in the next slides. Supervised fine-tuning, SFT in short, is a type of training which is performed with human annotated labeled data. For example, supervised fine-tuning, SFT, for question answering task uses human labeled question and answer pairs, as shown on the left image. The amount of fine-tuning needed depends on task complexity and dataset size. Image on right shows few examples of tasks for fine-tuning. For style transfer with GPT 3.5 or GPT-4, just 30-50 high-quality examples can be enough for strong results. In SFT, the model's weights are updated using gradients from the task-specific loss, which measures how close its answers are to the ground truth. This helps the model learn patterns and adapt its parameters to fit the new task. Let us see a concrete examples of SFT. An LLM model, after pre-training, does not yet have the ability to follow human prompts. It needs further training to understand and respond to human instructions. Instruction fine-tuning is a type of supervised fine-tuning that makes LLM follow human instructions. Instruction fine-tuning, IFT for LLMs, involves training them on datasets of instruction response pairs. The slide shows examples of task-specific data in the SFT input column and human annotated targets in the SFT target column. However, SFT data does not include task instructions. In the IFT input column, the task description is added to the same SFT input. For sentiment classification, the instruction is, classify the sentiment of the following. For grammar correction, the instruction is, correct the grammar in this sentence. This allows the LLM to learn what each instruction expects. At inference time, even if users only give instructions without examples, the LLM can still follow the instructions and produce the correct outputs. This approach helps the model bridge the gap between general language ability and following human commands. By training on instruction-based examples, the model learns to perform tasks more effectively, even with fewer prompts. The graph on the right shows that instruction-tuned models generalize better to new, unseen tasks than untuned models, especially as model size increases. Let's move on to discuss fine-tuning with reinforcement learning, RL in short. In RL, an agent learns by receiving positive or negative rewards for its actions. Here, the actions are the model's outputs, which get scored to show how well they meet expectations. Over multiple rounds of fine-tuning, the model updates its parameters to aim for higher scores. In supervised fine-tuning, SFT, the model simply tries to match the labeled answers, as shown on the left. In contrast, reinforcement learning-based fine-tuning, known as ReFT, encourages the model to reason its way to the answer, as shown on the right. A system of graders assigns a score, usually between 0 and 1, which guides the model's updates. Each time the model generates an output, it is graded, and this score acts as a reward signal, nudging the model's parameters in a direction that should improve results. This process is repeated, and model performance is checked on a validation set to confirm it is learning effectively and not just memorizing. ReFT offers several advantages over SFT. A key advantage is exploration. In SFT, the LLM learns to reproduce the chain of thought output token by token. In ReFT, the model learns to explore new chain of thought outputs that lead to the same correct reward. This exploration enables better generalization. By guiding models to actively reason through diverse solutions using reward signals, ReFT achieves superior generalization. This is essential for real-world tasks requiring nuanced problem-solving. This slide compares SFT and RFT across several perspectives, including data requirements and efficiency. Let's focus on data requirements. Creating detailed answer labels for SFT is costly and time-consuming, while ReFT only needs reward scores, making it less effort-intensive. Although ReFT training is slower than SFT, it yields better results. While SFT is useful for initial LLM training, ReFT helps models learn not just the right answers, but also the reasoning process behind them. In real-world scenarios, the best path learned during SFT may not always be possible, so the ability to explore alternative reasoning paths leads to better outcomes. By guiding models to reason through diverse solutions using reward signals, ReFT enables superior generalization, which is critical for real-world tasks that require nuanced problem-solving. This leads to more robust performance and adaptability, even when data is limited. Let's now see what are the various types of reinforcement-based fine-tuning. There are 3 types of RL-based fine-tuning. At high level, they differ in how the reward function is designed. ReFT, or reinforced fine-tuning, uses a rule-based reward model rather than a learned one. It is most suitable for objective tasks, such as math problems, where rewards can be determined by clear, rule-based criteria. RLHF, or reinforcement learning from human feedback, uses a learned reward model based on human annotated data. The reward signal is not mathematically precise or directly available, but instead comes from human judgment. This approach is ideal for subjective tasks, especially language tasks. RLAFE stands for Reinforcement Learning from AI Feedback. It is best for tasks where AI-generated feedback is both available and reliable. Let us dive deeper into ReFT, which is the simplest type of fine-tuning among the 3 types of RL algorithms. During LLM training, reinforcement fine-tuning, ReFT, is usually performed after completing supervised fine-tuning, SFT. ReFT consists of 2 main stages, the warm-up stage and the reinforcement learning stage. In the warm-up stage, the model is fine-tuned for a few cycles using question and chain of thought, COT pairs. This step is essential for teaching the model basic problem-solving skills, enabling it to generate reasonable responses to questions. The model learns to predict a sequence of tokens forming the COT, finishing with a special end-of-sequence token. By sampling actions from its policy and updating its state after each action, the model gains foundational accuracy in generating COTs. After warm-up, the reinforcement learning stage begins. Here, the model improves through online self-learning, using question-answer pairs. It samples responses, evaluates their correctness using a precise reward, and updates its parameters based on this feedback. The process often uses the Proximal Policy Optimization (PPO) algorithm. Rewards are assigned depending on how closely the model's answers match the ground truth answers, encouraging better performance. The bottom line is that Stage 1 teaches the model how to answer, while Stage 2 teaches the model which answers are preferred, rewarding any correct form, new phrasing, or added style directly. Let's consider scenarios where a precise reward function is not available. For example, when grading a poem, human preferences and subjectivity play a major role in deciding whether a poem is good or great. In these cases, designing a rule-based reward model is difficult or even impossible. Instead, we use human feedback to train a reward model. This is where reinforcement learning from human feedback, or RLHF, comes in. RLHF allows the model to learn preferences directly from human evaluations rather than relying on strict mathematical rules. Let's look into the premise of RLHF in more detail to make sure we understand it clearly. RLHF is used when a rule-based reward model is not available or is hard to design. Hence, the reward model itself needs to be trained before we can use it to train the LLM. The data for training this reward model can be collected from human feedback. Let us now look at the actual RLHF training steps. In Step 1, data for training reward model is collected using human feedback. For example, a Reddit post is sampled. Multiple summaries of the post is generated, and 2 are provided to human for feedback, which is better. Step 2 involves training the reward model. The reward model shares the same underlying architecture as the LLM itself. To train the reward model, we take pairs of ranked responses as input, predict the preference score of each response, and apply a ranking loss. See above. The purpose of this ranking loss is to train the regression-based reward model to output a higher preference score for the preferred output and vice versa. In this way, the reward model's training procedure aims to teach the model to accurately predict a human preference score given a prompt and response pair as input. Step 3. The trained reward model is used to score the output generated by the LLM based on current policy. This reward is used to improve the policy using PPO algorithm, iterative RLHF. Before moving on, we should note that RLHF is typically not only applied once. Rather, most works tend to collect data in large batches and fine-tune the model via RLHF in an offline fashion. This process is repeated several times as more data is collected over time, allowing several rounds of the RLHF process to be performed. This slide shows the overall summary of the RLHF. Human preference data is used to train reward model. The LLM is already instruction fine-tuned before RLHF. The generated output using current policy. The reward model provides a score for the output. This score is then used to improve the policy using PPO algorithm. There are several variations possible for the RLHF algorithm. It could be online or offline. The RL algorithm could be PPO or some other. Hyperparameters could be tuned differently. While RLHF has gained popularity due to use in ChatGPT, here are a few challenges that it faces. Since it involves humans, it is expensive. Additionally, human preferences evolve with time and varies across different humans, leading to inconsistencies. This is an interesting flowchart that helps to decide which algorithm to choose based on number of examples available and task verifiability. It is interesting to note that RL-based algorithms perform when examples are few and ground truth is also not available. Another feedback-based algorithm is reinforcement learning from AI feedback, or RLAIF. The main difference between RLAIF and RLHF is the source of feedback. In RLAIF, the reward model is trained using data generated by another AI model, instead of relying on human feedback. This reduces the dependence on human effort in creating training data. As a result, RLAIF is more scalable and can be applied to larger datasets or more complex tasks. As we begin understanding RLAIF, let us first understand what are the steps that are similar to RLHF. The key idea of RLAIF, that reward model, is also a LLM, and it is trained on feedback data is borrowed from RLHF, as shown in the left of image. The trained reward model is then used to score the output generated by the agent LLM model by evaluating its current policy, right of the image. Using this score feedback, agent LLM model improves its policy using PPO algorithm. These steps are similar between RLHF and RLAIF. However, the key difference lies in training data of the reward model, also called harmlessness preference dataset, on left of the image. In RLHF, this training data is generated by human labelers, whereas in RLAIF, it is generated using another LLM. Let's dive deeper to understand the generation process of this training dataset. In RLAIF, the training data for reward model is generated in two steps, as shown in the left of the image. In the first step on left, a LLM called SLKI is used to generate response to harmful prompts, such as answer A and B. In this step, the SLKI model acts as generator of response. In the second step, the same SLKI model acts as feedback model, comparing answer A versus B and rating which is better. Hence, there is no involvement of human, as both response and rating are both generated by LLM, making the process scalable. So what is SLKI model, and how is this generated? The SLKI LLM model is generated by supervised fine-tuning on revision dataset. This revision training dataset is also augmented by human-generated helpful question and answer dataset. Let us understand what is this revision dataset. Here is an example, steps for generating revision dataset. In the image on left top, the harmful prompts is used to generate answer using a RLHF LLM. As the initial answer is harmful, it is critiqued by another LLM to generate a revised answer. This process is carried out iteratively. The final revision of the answer is then saved with the harmful prompt as training data, as shown in the bottom image on right. It is important to note, harmful is a subjective concept and can mean different things to different people. So, let us understand what is the definition of harmful that guides the critique LLM. Just like constitution of a country or organization, the definition of harm is agreed among humans and is documented in a constitution. Here is an example of 3 different types of human values that is used to judge what is harm and what is not harmful. Fairness, transparency, safety, and security guide the critique LLM. It is important to note that human judgment is used to arrive at this constitution. Hence, constitution is the primary contribution of humans in the entire process of RLAIF. As shown in the left of the image, the RLHF trained LLM is used to iteratively generate response and critique by randomly sampling values from the constitution. Essentially, each response is revised iteratively based on each of the values in the constitution to ensure maximum alignment of AI with human values while ensuring minimum human effort. Overall, RLAIF is a scalable training process with minimal human involvement to ensure the final trained LLM is most helpful at the same time minimized harm. Scalability of RLAIF process allows more elaborate testing and better handling of diverse and edge cases. Congratulations, we have completed 4th major milestones of our journey in the agentic AI landscape. We just saw the topics on the right bottom of the AI landscape. Feel free to pause and take a quick break. Don't forget to come back because we will discuss distillation, the key breakthrough in which reasoning power is transferred from large to small model, is up next.